let's try to figure out just how far off our estimated value from the MLE might be from the truth. How far away is theta hat from theta? So we know that when we go and collect data, the MLE that we measure, our theta hat, is going to be wrong. It's most certainly not going to be equal to the true value of theta in the probability distribution, but we should be pretty close. So what we'd like to do is we'd like to measure, well, how far off do we think we are? How far off is our estimate theta hat likely to be from theta? We're going to call that quantity the standard error of our estimate. And then what's a range of plausible values for theta that are consistent with the data that we've collected? Can we come up with a confidence interval for theta based on our sample that we've collected here? And so what I mean by this is if we were to go and look to see what the possible values of theta hat that we might observe from one random sample to the next, we want to see, well, what does the shape of that sampling distribution look like? What is the shape of that probability distribution that describes the possible theta hats that I might see? So if I make a plot, it turns out that a lot of sampling distributions look approximately normal. What we can do is we can agree on some sort of reference point that looks like a good measure of how far off typically the estimated value theta hat might be from the true value. If the sampling distribution of our statistic is well described by a bell-shaped curve like what we see here, well, a logical place on that distribution to pick for measuring how far off the typical value theta hat might be from theta would be at the inflection point of that curve, where the curve goes from sloping downward quicker and quicker to sloping outward here. And in fact, that's what we're going to do. We're going to try to figure out where are the inflection points on the sampling distributions of our statistics. That's a good measure for how far off typically our estimated value might be from the true value of the parameter. And so our goal is trying to figure out where is that location. Can we come up with a numerical value for this standard error, the typical difference between our theta hat and our theta? Now, to give this full discussion fair treatment, we've really got to dive into the notion of sampling distributions of a statistic, because when we go and do this estimation procedure, we're going to have exactly one sample, one estimator, one theta hat, and we'd like to discuss, well, how far away might theta hat be from theta? So we kind of have to envision a universe with a whole bunch of other samples out there and how far away their theta hats might be from theta. The sampling distribution of a statistic is simply the probability distribution of that statistic when we go and collect a sample. What are the possible values for that statistic that we might observe, and what are the corresponding probabilities? So, quick review, a statistic is just some number that we calculate from a set of data values. So the sample average, x bar, is a statistic. The sample standard deviation, s, is a statistic as well. And so the whole theory of estimation and inference is built on the idea of the sampling distribution of a statistic. When we go and collect data, the statistic that we're measuring, like x bar or s, is going to vary depending on what set of data values we happen to collect. So what is the probability distribution of that statistic? What is the list of possible values of that statistic that I might observe? And what are the corresponding probabilities? What's the shape of that probability distribution look like? Now, the good news is we're actually kind of familiar with some sampling distributions already. We talked about the Bernoulli random variable, that very simple random variable that only has two outcomes, the success or failure, the 1 or a 0, with the success probability p. And we've talked about what happens if we were to look at a sequence of Bernoulli trials. If we were to collect a whole bunch of successes and failures, x1, x2, x3, etc., a bunch of 1s and 0s, and then sum all of those 1s and 0s up, well, we would get the PMF of a binomial distribution. The binomial distribution counts up the number of successes out of n trials. So we can say something about the sampling distribution of the sum of many Bernoulli random variables. The sum of n Bernoulli random variables is a binomial distribution with parameters n, the number of trials, and p, the probability of success. Likewise, we've talked about the geometric distribution. The geometric distribution is the number of failures until that very first success. So if we were to go and collect a bunch of data values from Bernoulli trials, a bunch of 1s and 0s, the geometric distribution is the sampling distribution of a very special statistic. Basically, if I go and look at my first data values, it's going to be the statistic, the number of zeros that I observe until that very first one, something I'm calculating from the data itself. And so the geometric distribution is the sampling distribution of that very special statistic. Now, there's one very famous sampling distribution that we should introduce, the sampling distribution of the sample average when we're pulling data from a normal distribution. So let's imagine that we're dealing with an IID sample from a normal distribution that has a peak at mu and a standard deviation equal to sigma, and we collect n values from that distribution. Well, if we go and calculate the sample average, that sample average is going to be tied into the data values that I happen to collect. If you go collect a different random sample, you'll measure something different for that sample average. It turns out that the sampling distribution of the sample average, the possible values of the sample average that I might measure when I go and collect data, is perfectly well described by a normal distribution in and of itself. It's going to have the same peak as the probability distribution making each individual value. It's still going to peak at mu. And it turns out that I can predict the standard deviation of the sampling distribution just by looking at the standard deviation of the normal that's generating the data. Take that sigma, divide by the square root of n, and that's going to tell you what the standard deviation is of that normal distribution, describing the possible values of that sample average that you might collect. And we can see this by running a Monte Carlo simulation. Let's imagine that we collect a random sample of size 25 from a normal distribution with a mu equal to 15 and a standard deviation equal to 3. And let's go and do this again and again and again and again so we can see what the variety is and the possible sample averages that I might collect. I can go and maybe do 100,000 different random samples, each of size 25, keep track of each of their sample averages. Well, if I look at a summary of the sample averages that I got over all 100,000 random samples, I see that that sample average is right at 15, the same average as the normal that was generating my data, and the standard deviation of that, best observed graphically actually, if I just superimpose the histogram of all those sample averages that I saw across those 100,000 different random samples, superimpose that normal curve that has the peak at 15 and the standard deviation equal to sigma over the square root of n, sigma being the standard deviation of the distribution that was generating the data, that 3 divided by the square root of 25, 5 in this case, we can see that the normal distribution with a mean of 15 and a standard deviation of 3/5 perfectly fits the distribution of those sample averages that I collected during my Monte Carlo simulation. And so that's going to be our goal here. We know that we can't do any better when estimating theta than with the MLE, especially for large samples. And so what is the sampling distribution of theta hat? What's the sampling distribution of the MLE? If I knew what that was, if I knew what possible values of the MLE that I might observe when I go and take a random sample, I'm going to be able to make some pretty strong statements about how far any particular theta hat might be, i.e. the one collected in my sample, how far that might actually be from the true value of theta. I can put probabilistic bounds on how far away it is, come up with not only an idea of a standard error, typically how far off my estimate is, but also come up with a confidence interval, a range of plausible values for theta based on the data that I collected. So here are the key insights about the maximum likelihood estimator. So it turns out that the sampling distribution of the MLE, the distribution of the MLEs that we might observe when we go and collect a random sample, is a normal distribution. And the key properties of this normal distribution is that the peak is at the true value of the parameter we're trying to estimate. The peak is at theta. And it has a standard deviation that I can predict from the Fisher information itself. In fact, the standard deviation of that sampling distribution of the MLE is just the square root of 1 over, and then in the denominator, the sample size times our expression for the Fisher information evaluated at theta being equal to the maximum likelihood estimate. So let's just see where all this comes from with an actual example. Let's imagine that we're studying the times to failure of hard drives. So let's imagine that the time to failure is memoryless, so that an exponential distribution is going to do a good job at describing the probability of different lifetimes. In that case, I know that I'm dealing with a PDF that has the following equation. lambda times e to the minus lambda times x. That's my equation for the PDF of an exponential distribution. And so I would like to estimate lambda here from a random sample of data values. So let's imagine that we've taken a random sample of size 150. We have the failure times of 150 hard drives. We want to use that to estimate lambda. And not only that, but we want to figure out how far away might our estimate be from the true value of lambda that's generating our data, and make some pretty conclusive statements about, how far off I think I might be here. So looking at a summary of the hard drive failure times, we find that the average is right about 4.4, but there's a pretty big variety going from 0.014 all the way up to over 21.3. And so what do I need to measure about this data to come up with the best estimate for lambda? Well, we've done this exercise in the past. It turns out that the maximum likelihood estimator for lambda for an exponential distribution is just the reciprocal of the sample average. So the average was 4.412. Take the reciprocal. Our good guess for lambda is right at about 0.2267. So we obviously know that our guess isn't going to be correct. The true value of lambda is probably going to be close to this number, but just how close is it going to be? Well, let's explore something about the sampling distribution of the MLE when we go and take a random sample from an exponential distribution. So in this case, I generated this data with an exponential distribution that had a lambda equal to 0.2. So what if the data values came out a little bit different? What if I had a different set of 100 random values from this distribution? What kind of variety in the sample averages, and therefore variety in the MLEs, might I actually measure? So let's go and consider taking 5,000 different random samples, each of size 150, from this exponential distribution, and just looking at that sampling distribution of the MLE. What kind of variety do I see from one sample to another of the reciprocal of the sample average here? So if I measure the MLEs for each of those other random samples, I find that they're fairly tightly clustered around 0.2 or so, but there is some variety going down to about 0.15 and going up to about 0.28. Now, if I make a histogram of all of those MLEs across those 5,000 different random samples, I find something that resembles a normal curve. It looks nice and bell-shaped. I've drawn the red line to represent what the MLE was for the originally collected data values. And in this case, I see I'm pretty close. And I'd like to develop some sort of broad statement about, all right, just from my one random sample that I've collected, my one value of theta hat here, or one value of lambda hat, how far off do I think I might be from the true value of lambda? And so what we'll do is we'll exploit this normality of the sampling distribution of the MLE. If we were to go and compare that histogram of those 5,000 different MLEs that we've measured from 5,000 different random samples, we see a pretty close correspondence to the normal distribution via comparing the QQ plot. So let's build off that. It turns out there's a key theoretical result that says for really big samples, the sampling distribution of the MLE actually is normal. And so let's go with this. So if the sampling distribution of the MLE is normally distributed, what can we measure about that normal distribution that would be a good stand-in for a typical difference between what I might observe in any one particular sample, a particular value of lambda hat, and the true value of lambda that's generating the data? Well, one common feature of all normal distributions is the distance from the peak to the inflection point of that normal curve, where that curve goes from sloping downward ever more quickly to sloping outward ever more gently. And so it turns out that that location is the standard deviation of that normal curve. All normal curves have that property where that inflection point occurs at exactly one standard deviation away from the peak. So that's a pretty good reference point on the normal curve. Let's go ahead and use that measure, the distance from the peak to the inflection point, as a measure of our standard error of our estimator, the typical difference between the values we might observe on a sample and the true value of lambda that's generating the data. So we're going to use that measure as our standard error, our best guess of how far off our lambda hat might be from lambda in this case. the question becomes, how do I actually get that distance? How do I figure out the distance from the peak to that inflection point with just the one sample that I've collected? So theory says, well, there's actually a formula for that. You can write out the formula for the standard error in terms of the Fisher information of the probability distribution, which requires you to calculate second derivatives, expected values, so it's a bit of work mathematically. But there is a formula to go and actually do that. And so once we've collected our one random sample, there's going to be a formula that lets us know what the standard error is of our MLE. Our best guess at how far off our MLE might be from the true value of the parameter of that probability distribution. It just takes a bit of mathematics to get there. So if I wanted to go through this calculation with the exponential distribution, here's how I would do it. I would write out the formula for the PDF of the exponential, theta times e to the minus theta times x, just replacing the lambda by theta, my generic placeholder for the parameter. Then I'd take the logarithm of my formula for the PDF, and what I'd find is that the formula for the log is just log of theta minus theta times x. So Fisher information says, okay, we'll take your expression for the log of f, take that derivative with respect to theta, then take that expression, take its derivative with respect to theta. That'll give you some sort of function, figure out the expected value of that function. So we know how to calculate expected values of functions. What we do is we transcribe our formula for that function, in this case just minus 1 over theta squared, times the formula for our PDF, which is the formula for our exponential, and then we integrate that over all possible values of x that we could potentially observe. So I'll integrate that expression, minus 1 over theta squared, times theta times e to the minus theta times x here, my formula for the PDF, from x equal to 0 all the way up to x equal to infinity. And what I find is that that's equal to minus 1 over theta squared. Fisher information says to flip the sign of that expected value, and then you get the Fisher information. So the upshot is that I found that the Fisher information for an exponential distribution is just 1 over theta squared. So if I want to know what the standard error is of my MLE estimate, all I need to do is take 1 over n, my sample size, times the value of that Fisher information evaluated at the MLE estimate. And remember, theta MLE for an exponential is just the reciprocal of the sample average. And so I would replace that 1 over theta squared by the 1 over x bar squared, giving me x bar squared here for my estimate of the Fisher information, throwing those into my formula for the standard error, and I find out that in general, my standard error formula for the lambda parameter of an exponential is just the square root of 1 over the sample size times the square of the sample average. Kind of a nice simple rule to know what you need to do to figure out how far off your best guess might be. And so we can compare that formula to what our Monte Carlo simulation suggested that we would see. So if we plug in the sample average of our originally collected sample into the expression for that standard error, what we'd find is we get a value of about 0.0185 out. If we were to go and look actually at the standard deviations of those 5,000 different MLEs that we collected during our Monte Carlo simulation, we get about 0.016. So actually pretty darn close. And quick little preview here, if you were to just fit dist on the original set of data that we collected, fit that to an exponential distribution, what you'd find in the standard error column of the output of fit dist is that 0.0185, the exact value of the standard error formula when we went and plugged in the value of our sample size and our sample average. So we're going to see actually that we can bypass this math very quickly and just use fitdist, which is the good news. But it's kind of like a nice little warm hug that there is a mathematical expression that lets you know how far off your MLE might be from the true value of the parameter involved in the probability distribution that's generating your data. So Fisher information statistical theory unlocks an ability to figure out how far off our MLE might be from its true value from just that one sample that we've collected. Kind of exploiting the fact that we know something about the sampling distribution of the MLE, the possible values of the MLE that we might measure when we go and collect a random sample. Now, here's another way to come up with the formula for the standard error, or at least a numerical value for that standard error, that you might find equally appealing. So when we get the MLE estimate for lambda for an exponential distribution, we write out the likelihood and then figure out what value of lambda makes the likelihood reach its peak. So writing out the likelihood just involves writing out n copies of that PDF, multiplying all those copies together, and then grouping terms. In this case, we would find that the likelihood is equal to lambda to the 1/50th power for the data that we've collected, 150 data points, lambda raised to the n. And then we'd have a times e raised to the minus lambda times 661.78. It turns out we need to take the sum of all the x's to put in that exponent. And so when we plot that likelihood, we find that it reaches a very well-defined peak. And where it reaches the peak, that's the MLE. That's the value of lambda that gives the resulting probability model the highest chance of producing the data that we've collected. And so that's the 1 over the sample average. That's how it worked out to be. But we do see, based on the plot of the likelihood, that there is a little bit of leeway to the value of lambda that we could take. Other values of lambda a little bit higher than the peak, a little bit lower than the peak, result in a probability model that sure has a slightly lower probability of producing our data, but it's not that much lower. We do have a little bit of leeway. So why don't we do the following? Why don't we try to figure out, well, what's the distance between the overall peak of that likelihood and where the inflection point of that likelihood is, where the likelihood goes from sloping downward ever more quickly to sloping outward ever more gently. Kind of like how we decided what the standard error should be when we referenced that normal distribution, looking at that inflection point of that normal distribution. Why don't we do something similar here and use that as kind of the amount of leeway that we have in our estimate of that lambda parameter for the exponential? Well, if we want to go and find out where that inflection point is, we need to go and ask Wolfram alpha, hey, where does the second derivative of my likelihood equal to 0? Inflection points are where second derivatives of functions are equal to 0. And Wolfram alpha can do that really with very little problem. And it says, okay, the inflection points of your likelihood occur at a value of lambda of 0.208 and a value of lambda of 0.245. So why don't we use the distance from the peak, the MLE, to these inflection points as a measure of our standard error, how much leeway we really have in our estimate of lambda? Well, if we do this, if we go and measure where the peak is, taking the reciprocal of the average value of the data that we've collected, looking at the distance between the peak and those two inflection points, we see that the inflection points are about 0.0185 away from the peak. And wouldn't you know, if you go and use the Fisher information expression, if you use fitdist, that's the exact same value you get out for the standard error. So this provides us another way of thinking about what the standard error of the estimate actually is. When you plot that likelihood, sure, we're going to take as our best guess for lambda where that likelihood peaks. But we do have a little bit of leeway. That standard error, our best guess for how far off our lambda hat, the MLE, might be from the true value of lambda, can be taken to be, that amount of leeway that we have with that estimate. How far away can we go from the peak of that likelihood before we run into one of those inflection points? And so we've discovered a great alternative interpretation of what the standard error of our estimator is. Now, the normal interpretation is that when we go collect a single set of data, we'll measure a single MLE. The standard error tells us our best guess for how far off that MLE might be from the true value of theta involved in the probability distribution making our data. And that standard error is found by kind of imagining, well, what's the sampling distribution of the MLE? What are the possible values of the MLE that I might measure when I go collect a random sample from the probability distribution? What's the typical difference between the possible MLEs that I might measure and the true value of theta? That's the standard deviation of the normal distribution associated with the sampling distribution of the MLE. And so this likelihood approach provides an alternative way of interpreting that standard error. It simply says, okay, we'll take our MLE to be the place where the likelihood peaks, but there's a little bit of leeway. Larger values of lambda, smaller values of lambda, result in probability models that have a slightly smaller chance of producing the data that you've collected, but not by much. And so if we use as our leeway just where the inflection point is of that likelihood, the distance from the peak to that inflection point gives our amount of leeway. Another way to think about what the standard error is, how far off, how much leeway we have with our estimate. And so at this point, we can discover really one of the most important formulas in all of statistics, in all of inference. Very often, we're just trying to estimate the probability of some event occurring. We've spent lots of time running Monte Carlo simulations to estimate the probabilities of complex processes. And at the end of the day, once our Monte Carlo simulation concludes, we have an estimate, we have a p-hat, but we'd like to know, well, how far off is p-hat going to be from p? How wrong are we after our Monte Carlo simulation is concluded? So let's develop the formula for the standard error of p-hat. What's our best guess for how far off our p-hat that we've measured, say from our Monte Carlo simulation, how far off that might be from the true value of p, the true probability of our event occurring? So what we can do is we can try to derive the formula for the standard error that uses that Fisher information. So we can write out our expression for the log of the PMF that we're dealing with, just a Bernoulli PMF because each trial is a 1 or a 0. And if we take the first derivative with respect to p, the second derivative with respect to p, we can get an expression for a function whose expected value we have to evaluate. So in this case, what we need to do is figure out the expected value of the expression minus x over p squared minus the quantity 1 minus x divided by 1 minus p squared. We'll take our formula for this expression, multiply that by the formula for our PMF, and in this case, since we're taking a discrete quantity x here, we need to sum up those values over all possible values of x. Integration is for continuous quantities, sum is for discrete quantities. We only have two discrete quantities here, so 0 and 1, summing that expression from x equal to 0 to x equal to 1. And so what we find is that our expression for that Fisher information is just 1 over p times 1 minus p. And it turns out Wolfram Alpha can do this evaluation in just one line. So if you're good enough writing and transcribing expressions, you can get Wolfram Alpha to immediately just give you what that expression is for that Fisher information. But once we have that Fisher information, we can immediately write down what our formula is for the standard error. So how far off is our p-hat that we measured from a Monte Carlo simulation likely to be from the true value of the probability of our event occurring? Well, the formula for the standard error is the square root of 1 over the sample size n, the number of Monte Carlo trials that we performed, times the Fisher information evaluated at our maximum likelihood estimate. So that Fisher information is 1 over p times 1 minus p. So the quantity 1 over n times the Fisher information is just p times 1 minus p over n. Taking the square root of that and replacing the p's with our p-hats, we get the very well-known and famous formula that the standard error of an estimated probability p-hat is just the square root of p-hat times 1 minus p-hat over n. So if it ever kept you up late at night wondering where does that formula come from, where does that magically materialize from, well, this is where it's coming from. It's coming from the analysis of the Fisher information of that Bernoulli PMF that's generating the 1s and the 0s associated with our Monte Carlo simulation. Now, we could also get this same expression from the examination of the likelihood. If we were to go out and write out, say, the likelihood of a random sample that we've collected, let's imagine we were running a Monte Carlo simulation to estimate the stockout probability under some inventory control policy, and we found that after 1,000 trials, a stockout occurred in 90 of them. Well, the likelihood in that case would be 1,000 choose 90 times p raised to the 90 power times 1 minus p to the 910 power. The total number of successes, total number of stockouts out of 1,000 trials is a binomial distribution, so just writing down the formula for the PMF of binomial. Now, we know that the p-hat is just the fraction of trials where our event occurred, so 90 out of 1,000, the average of the 1s and 0s that we essentially collected during that Monte Carlo simulation. And so let's look at that likelihood. So if we make a plot of that likelihood, we see that, okay, it's peaking right at around p of 10% or so, really at p of 9%, the fraction of trials where our event of interest occurred. So let's go ahead and zoom in. Once we do that, we see that, okay, sure, the value of p that maximizes that likelihood is right at about 0.09, but we do have a little bit of leeway. If we took a value of p a little bit above or a little bit below, sure, that results in a probability model that has a smaller chance of reproducing the data that we collected, but the chance isn't all that much smaller. So let's use as our measure of leeway the distance between the peak and where the inflection point is on that likelihood. So where it goes from sloping downward ever more quickly to sloping outward ever more gently. And so we can ask Wolfram alpha, where do those inflection points occur? And after throwing that into Wolfram alpha, we get some answers. We get 2 inflection points. They kind of look like 9 over 100, that 0.09, the location of the peak, plus or minus something. So upon further investigation, if we look to see, well, what is the distance from the peak to each of those inflection points, what we find is that that distance is 0.009. And that just happens to be the exact same value when we go and take the square root of p hat times 1 minus p hat over n. And so we have that nice correspondence. The formula for the standard error that we get out, using that Fisher information, using that formula for the standard error, works out to be basically the exact same number as if we were to go and measure the distance from where the likelihood peaks to where the likelihood has those inflection points. So that's a lot of math to get the formula for the standard error with either the likelihood approach or trying to work out what that Fisher information is. So how are we actually going to get standard errors in practice? Well, we can suck it up and just do that math, but there really is a much better way to go about doing this. Because fitdist goes and does a search for where that likelihood peaks numerically, along the way it's going to figure out where those inflection points are of that likelihood. And so what we can use is the results of the search that fitdist is doing to come up with a measure for the standard error immediately. Fitdist will not only measure where that likelihood peaks, but it will measure how far away those inflection points are from the peak of the likelihood, and we can take that to be our measure of the standard error. And so our problem boils down to something as simple as just running fitdist on our collection of data values with the probability distribution that we have in mind. So once we get the value for the standard error, how do we interpret it? How do we add value to this analysis? Well, the standard error is our best guess for how far off we think our MLE is from the true value of theta, associated with the probability distribution that's making our data. So we know that when we go and collect data, the value we measure from our MLE is going to be wrong. It's not equal to theta exactly, but it should be close. And we think that our estimated value, the MLE, is going to be off from theta by about a standard error or 2. So we could say we estimate theta to be theta hat, the MLE, give or take a standard error or so. Now, most of the time we'll be using fitdist to get those standard errors. So when I go and fit my hard drive failure data to an exponential distribution, I come up with the MLE that lambda is equal to 0.2266. It's not going to exactly equal to lambda. It's going to be close. How far off do I think I am? Well, I think I'm probably off by about 0.0185 or so. So I estimate lambda to be 0.2266, give or take 0.0185 or so. So I think the most efficient way of getting the standard errors of the MLEs is just to use fitdist. And we can set this up the same way as when we set up fitdist to estimate the MLEs. What we'll do is if we have a notorious distribution, just use the name of that notorious distribution in quotes when we use fitdist. If we have a custom distribution, we'll define dcustom. The first argument will be named x. The second, the third, etc. arguments will just be the names of the parameters of that distribution. Inside the curly brackets of dcustom, you're just going to transcribe the formula for your PMF or your PDF. And then you're just going to run fitdist. First argument is going to be your vector of data observations. Your second argument will be custom in quotes. And then you'll give it a little starting push, a reasonable place to start looking for the MLE estimates. You'll define your start list equals. So for each parameter in your distribution, you'll give it a starting value, and fitdist will take it from there. And once you get a summary of the fit, not only will you get the MLE, that value in the estimate column of the output, but then you'll also get a value for the standard error, how far off we think that estimate might be from the truth.